Thank you very much. Okay, well, assuming that my voice holds out, what today's lecture is going to consider is how our auditory system is able to use information about sound to tell us about objects and events in the outside world. And as we'll see, it turns out that a number of the principles that have appeared to be important in hearing also are known to be important in vision. But I should begin with a few basics about the ear and hearing first to set the scene. Here's a schematic of the human ear. Sound is collected and funneled in through the external ear, travels down the ear canal and sets the eardrum into vibration. These vibrations then travel through the chain of ossicles, the tiny bones in the middle ear, and the vibration pattern enters the inner ear. Now, the structure that will be key for us today is the cochlea, which is this snail-shaped structure from which the auditory nerve passes to the brain, containing about 28,000 nerve fibres in a normally hearing adult. So let's consider what the cochlea does in a little bit more detail. Basically, running all the way along the length of the cochlea on the inside is a structure called the basilar membrane. And the basilar membrane changes its properties in a smooth and progressive manner from one end of the spiral to the other. So at the base, it's very narrow and stiff, and it progressively widens and gets more elastic as we go up, spiralling up to the apex at the top. Because of this change in physical properties, the membrane prefers to respond to different frequencies at different places along the cochlea. So the basal region, the narrow and stiff part, responds well to high frequencies, whereas the more elastic and wide part at the top responds best to low frequencies. Now, in real-life listening situations, we very rarely hear sounds that consist of a single frequency component. Rare exceptions would be things such as a vibrating tuning fork or a ringing wine glass. But most of the sounds we're exposed to contain many frequency components. And if you think of the way the cochlea functions in this regard, it is effectively a frequency analyzer. What it does is it breaks up complex sounds into their frequency components, and different places along the length of the cochlea respond to the frequency content of that sound. So effectively what the cochlea conveys to the brain is information about the frequency content or spectrum of complex sounds. So if we consider this complex waveform at the bottom, effectively we can make this simply by adding together these simpler vibrations which are shown further up here. So this sound here, I'm not sure how the volume will work here, but we'll try it, is actually composed of these simple vibrations added together. And you put them together and you get this. And this complex sound has a pitch which corresponds to its lowest frequency component, known as the fundamental. Now, having introduced the concept of pitch, I also want to introduce the concept of timbre or tone quality. One of the key factors that determines the quality of sound, what allows us to recognise it, is the way energy is distributed across the frequency spectrum. So what's shown here is a picture of two spectra, one for the vowel E, one for the vowel R. You can see the intense components here forming peaks in the spectrum as we go from lower to higher frequencies. And these two vowels sound different from one another precisely because the energy is distributed differently across the spectrum. The peaks in the spectrum are in different places. Similarly, the timbres of musical instruments depend on how energy is distributed across the spectrum. So if, for example, I focus on the timbre of the note from a bell, I can artificially build it up component by component from the low frequency end, and you should hear the timbre of the bell gradually emerge and become brighter as the higher frequency energy is added. So, just for fun, to emphasise this distinction between pitch and timbre, I'm going to take the voice of an esteemed auditory researcher from the UK, Chris Darwin. This is a process sample of his voice.
Could you please write the word bead down now?
Now, what we can do is we can artificially raise its pitch, which would be the equivalent of making the vocal cords vibrate faster, and the voice will sound like this.
Could you please write the word bead down now?
If, on the other hand, we leave the pitch fixed, but we shorten the vocal tract, which the average adult woman has a vocal tract that's only about 5/6 as long as an adult male, we get a change instead in the timbre.
Could you please write the word bead down now?
And if I combine both together, we can turn him into Christine Darwin.
Could you please write the word bead down now?
So, having introduced some of these basics, what I want to do now is to sort of broaden the scope and move more towards my thesis today, which is to ask the question, what is perception for? Well, there are various ways of answering that question, but I think a reasonable way to answer it is to say that perception is the process of building useful descriptions of objects and events in the outside world. We haven't got sensory systems for nothing. We have them because they're supposed to tell us about objects and events in the world that can be used to guide our behaviour. And as such, perception is not simply about processing incoming sensory information. It's a constructive process too. Now, some of you may not have seen this picture before. If you haven't, you may not even be able to see the figure in it. I'll give you a few clues. There is in fact an animal in this picture, and there's the ear and the head, the collar, the run of the back, the tail, one of the back legs, the other one. I'm hoping that most of you by now can see something akin to a Dalmatian in the middle of that picture. There's the one foreleg, there's the other one. Now, what's happened here is the photograph has been degraded to the point that the process of perception has been slowed so that you can see what's happening. You don't instantly see the Dalmatian unless you've seen it before. It's a constructive process. It relies on an interaction between the incoming sensory information and your stored knowledge in the brain about objects and events in the world. Now, in most real life situations, the sensory information we receive is partial, it's often degraded or ambiguous, and stored knowledge is often very important in our ability to perceive what's going on in the world. Now, a key part of this process, which will be the main focus of today's talk, is the process of evidence separation. It's very rare for us to see or hear a single object or event at the same in isolation. Normally they're heard in the presence of other sounds or seen in the presence of other objects. And one of the key things that our sensory systems have to do to be able to perceive and recognise objects is to separate which sensory evidence comes from which source or object and which comes from another.